Hello everyone. In this video, I will talk about the concept of vectors in physics. We know that there are two kinds of quantities in physics. One kind of quantity has just magnitude, so it's a pure number, and these kind of quantities are called scalars. And they have only magnitude. So in language that is easy to understand, magnitude means a number. So it's purely a number. Now here's an example. Let's say when we talk about mass. Mass in physics is a scalar, and it only contains a number. So now let's say this object weighs 1 kilogram. So 1 kilogram is a pure number, and it has no sense of direction. Okay, so now let's talk about vectors. Now vectors are quantities that have both magnitude and direction. And magnitude, just like a scalar, is just a number. But these kind of quantities also have the sense of direction. And different directions will make these quantity different. So let me give you one example. Let's say when we talk about how fast an object moves, we define a quantity called velocity. And velocity is a vector. Means that when we talk about how fast an object is moving, we need to say, let's say 10 meters per second. And also, by the way, meters per second is the unit for velocity. And just like before, kilogram is the unit for mass. So every number in physics should have a unit. Now, this velocity, 10 meters per second, is just a number. And when we talk about 10 meters per second, we don't know what direction the object is moving. It could move, let's say, along in north direction, along south direction, along east, or along west. So you don't know actually the object's motion direction. So that's why we need a direction here. So now let's say I want to say 10 meters per second east. Then that will mean this object is moving toward east. So that's the direction. Now we have a complete information about this object's motion. Okay. Otherwise, we don't actually know what direction the object is moving. Now, to compare with this vector quantity of velocity, let's talk about another physical quantity very similar to the velocity. It's called speed. Now, when I say speed, it's like in everyday language. So now let's say you're driving at 10 meters per second. If you talk about that, then that's the speed. Okay, and then speed is a scalar. And it does not have the sense of direction, unlike velocity, where we need to specify the direction. The speed here now has no direction. Okay, so that's the difference between scalar and vector in terms of everyday language. When we say speed in everyday language, we only talk about scalars. Okay, so now some other physical quantities, let's think about whether they belong to scalars or vectors. So now let's say when we talk about distance. That's another everyday language. When we talk about distance of the trip, we actually talk about scalars. So now let's say I traveled a distance of 200 miles. Then they only specify a number without saying the direction of that trip, right? I don't know whether I go south or whether I go east. I'll go another like in a curved path, right? Distance could be a curved path. Let's say I'm going along this curved path, and the sum of all these curved length, which is called arc length, is 200 miles. So the total here is 200 miles. But when I talk about another physical quantity, let's say displacement, then that is a vector again. It's a vector quantity again. So when I say I traveled 200 miles east, then I know exactly both the total length and also the direction traveled. Okay, so let's use the previous picture as an example. So here is your, let's say that's your home, and you start at your home and then you go, you drive along this curved path to the destination. Now you can say the same thing. Let's say I'm going to say the displacement. So the displacement now is going to be this straight line. So it's not a curved path anymore. It should be a straight line pointing from the origin, your starting position, to the final position, your destination. And it's a straight line that also has a direction going from the origin, your home, to your destination. Okay, that direction is east. Okay, so I hope that makes sense to give you the concept, the different concept of distance and displacement in terms of the difference between scalars and vectors. And again, a lot of physical quantities are vectors in physics. And in the next, I'm going to talk about some operations, numerical operations we can do with vectors, which are different from the scalars operations. And after that, you will see the vector, the concept of vector is like a natural translation of this kind of motion, the object's motion, and you will see the convenience of it. So again, the reason we introduce these vectors is for the both convenience and also the exact description. Convenience and exact description of the object's motion. Okay. All right. So let's talk about vector representation. So we know that a vector contains both magnitude and direction. So how to represent both of them? We can do in two ways. One is that we can draw it in a picture. So now let's say I draw an arrow like this. Then the length of it will represent the magnitude. So the magnitude is represented by the length of this arrow. And the direction is represented by this arrow direction, right? Exactly this arrow direction. Let's say arrowhead. The orientation of this arrow's head represents the direction of the vector. Now, another way of representing a vector is by this symbol here, by two numbers inside a parenthesis. So on this side, open parenthesis, the left open parenthesis side, we have, let's say, a number, let's say 10 meters per second. Okay. Now the right side here will represent the direction, right? The first one is the magnitude. Now this one is the direction. Then we want to say some angle. Let's say 20 degrees. Okay. But we need to define these 20 degrees. 10 meters per second for the magnitude is easier to understand. We can say the total length here, that is 10 meters per second, represent number 10. Okay. But how about this angle? When we talk about angle, we need some reference direction. So here's the reference direction. Let's say we use the east as the reference direction, which is this dashed line. Reference direction. And then this angle of this arrow with respect to the reference direction, that is 20 degrees. Okay, so let's summarize here. So we need in this representation a number here to represent the magnitude, and another number here to represent the direction, which is usually some angle, the degrees of angles with respect to a reference direction. That is the representation of vectors in 2D. Now think about some other ways of representing this arrow. So we know in mathematics you can have a Cartesian coordinate, such as this picture. So let's say I have a 2D Cartesian coordinate that has x and y axis. The origin is here, that's O. And if I draw an arrow, like in the previous picture, and I have the magnitude, let's say 10 meters per second, and then the angle here is 20 degrees. With respect to this x-axis now act as a reference direction. Then I have a representation that I described earlier. However, since we have x and y axis, we can have some other representations. So let me try to draw a vertical line to the x-axis and a vertical line to the y-axis. Now that is called projections. So we draw projections into x and y axis. And these projections, or the dashed lines, they intercept the x and y axis at some position. And these 2 points, they have some distance to the origin. And let's call this x coordinate, and that's y coordinate. Okay, so basically we're doing this just like in mathematics. So we have a point here that has coordinate x and y. And if I specify these x and y with the knowledge of the origin O, then I can totally determine a vector pointing from the origin O to the point xy. So that is called a vector's representation in Cartesian coordinates. Okay, so let's think about how to write down x and y using the previous knowledge of the magnitude and direction in the previous representation. And let's give this previous representation some symbol. Let's say the magnitude here is, let's call it A, some general vector A, and then the angle here is theta. Okay, so now this distance will be A from O to xy, point xy, and the angle theta will be this angle. So the x and y representation, its x is then given by this length, which is A. Now we call it A. Multiply cosine theta. So now we need some trigonometry from high school physics, from high school math. So the cosine theta here represents this adjacent of this angle theta. And A here is hypotenuse. Now the y component is A sine theta, which is the opposite side of the angle theta. That's this side. So now we know this representation in the 2D Cartesian coordinate for the vector is given by A cosine theta and A sine theta. Again, the angle theta is with respect to the x-axis, which is the reference direction I mentioned in the previous picture. Now let's also give the previous representation a name, a kind of a name. Let's call this polar representation. A vector's polar representation will represent this A, the distance from the origin, and theta, the angle with respect to the x-axis. Okay, now this representation is the Cartesian coordinates of the same quantity. Now that's the vector representation in 2D. Now in 3D, we have a similar representation. We can have two kinds of coordinate system to represent a vector in 3D. The first kind is called is using spherical coordinate. And then the second one is again Cartesian coordinates in 3D. Okay, so now let's look at the spherical coordinates first. So first I need a three-dimensional coordinate system x, y, and z. Here's the origin O. Okay, so now I'm looking at a vector. Let's use a different color. A with magnitude A, and it's pointing this way. So now I'm going to represent this A here with two other angles besides this magnitude. Let me first draw a projection of this A, this arrow, on the xy plane. So here's the projection into xy plane. Okay. So you have a it makes a intersection, a crossing point with the xy plane. Now we can connect from origin O to this point. Let me again use dashed line because it's an intermediate object. It also has a direction, like along this direction. Okay. Now I need to do a further projection. I need to project this dashed line vector into, which is two-dimensional vector, into x and y plane, just like what we did in the previous picture here. Now here's the projection perpendicular to the x-axis. Now that gives us an x, a coordinate x. Now this quantity's projection to the y-axis give us a quantity y. The intersection here is y. So that's like in 2D plane. That's what we discussed earlier. Now the difference now, because it's 3D, so we also have a projection from the original vector, this vector A, into the z-axis. And that gives us a z coordinate. Okay, so this point, the vector A here, represent x, y, z, right? But we can also use two other angles to represent the same quantity. So let's see, these other angles are, two other angles are, the first one, this angle, right? So let's call this angle, let's give it a name, let's say theta. And the angle with respect to the z-axis, let's call that angle phi. So now in 3D, we can represent a vector A with magnitude A, direction theta, direction phi. So we need two angles to represent its 3D direction. Now A is still just like before, the magnitude. Okay, so now we can easily talk about the conversion from these spherical coordinates to the Cartesian coordinate. Since we know the z here is given by a cosine phi, okay? So that's the easiest one to figure out first. Now the second quantity, let's say x, come from, first we project a to this opposite side, which is a sine phi, and that is the same as this line. Now I need to further project it to the x-axis, cosine theta. Now the y direction is a sine phi sine theta. Now we have the 3D Cartesian coordinate representation x, y, z, their conversion from the spherical coordinate a, theta, and phi. Okay, so that's the representation of vectors, various vectors in 2D and in 3D. And then let's also define something here called a negative negative vector. Now with that, we'll talk about next time how to do operations between vectors, and then we'll use the concept of negative vectors. So what's the definition of negative vectors? So we know previous arrow represent, let's say, a vector A. Now if I reverse the direction of A, or if I rotate this vector A by 180 degrees to the opposite direction, then we have this negative A. That is the definition of negative vector. Now in terms of the representation, we know previously A and theta represents the vector A. Now if I want to represent negative A, then since it still have the same magnitude, so I can say A, I can still say A, but now the angle here, we need to be careful. So originally it's theta angle with respect to the reference direction. Okay, so now on the top of that, I need to add 180 degree. So it's pi plus theta. That represents the negative A. Okay, so that's all for this video. And next time we'll talk about how to do operations between vectors. And from there, you will see the convenience of using vectors to represent an object's motion.